Hello, good afternoon to everyone. Thank you that you join us to the 11th conference of speech processing. This time it will be as a webinar, but I hope you will all join us and be happy from this new format. I want to invite for greetings our first head of our center, ACLP, and the current president of Afeka College, Professor Ani Moyal.
Thank you. Welcome, everyone, to the 11th Afeka Speech Processing Conference and the first to be held online. Hope that next year we'll come to the regular scenario. I'm happy to see that so many people from the speech processing community in Israel and abroad has taken the time to participate in the conference. I would like to thank especially Professor Vered Aronson and Dr. Itshak Lapidot for putting together the conference program, and to Afeka's events department for organizing the conference. And of course, thank you and welcome to Professor John Hansen from the University of Texas, our distinguished keynote speaker, and to all the guest speakers. 11 years ago, Professor Vered Aronson and I founded the Afeka Center for Language Processing, and within the first year, we already held our first annual conference. I'm happy and proud to see that our vision of becoming a hub for the speech processing community in Israel with strong global connections has become a reality. The center has grown over the years and has become a leader in research in speech processing in Israel. We started with research in the field of human-machine interaction, moved to security-based application, monitoring, education market, and recently to applications of the speech processing technologies and machine learning in the medical market. This has reached a peak over the last 3 months where we participated, all the Afeka Center researchers, in a national project led by the Ministry of Defense trying to pre-diagnose potential carriers of the coronavirus. I'm very happy that this Israeli project has emerged to a pan-European project with a cooperation of hospitals, universities, and high-tech companies in many European countries, among them Italy, UK, Romania, Netherlands, Czech, and others. Thank you again for everyone involving in bringing this conference together. I wish you all a successful event. Thank you very much.
Thank you to Professor Moyal. And now I invite Professor Vered Aronson, the head of Afeka Center for Language Processing, to say a few words.
So good evening and good morning, everybody. I'm delighted to host you here in our digital conference this year. After a semester of teaching, collaborating, meeting, and researching in this manner, it seems bizarrely natural to do it. But I joined Professor Moyal in hoping that next year we'll resume our normal physical conference as in last year, the last 10 years. I would like to mention that in addition to this conference, we have a second conference for the last 5 years, which is speech processing for healthcare. This is not only because in the last 3 months, our entire team was committed and worked on the COVID detection project, but also as heads-on, as next year conference will be a merged conference of the major one, this one, the processing conference, and the healthcare speech processing conference. It will be next June, and I hope to see you all in this conference as well. I would love to end by mentioning something that I heard last week in a medical conference. One of the doctors there said, you know, it's a miss term to say social distance. it actually should be physical distance. It's the physical distance we should keep. But socially, we must be more united and connected than ever. And I hope that all of us, the speech community in both industry, military, and academia, will be as united as in last year and bring on the next evolution and revolution of speech processing. Thank you very much. Happy to see you all.
Thank you, Vered. And before we will start the first talk, you will be able to write in the chat questions and during the talks, and we will read some of them and get answer. I apologize if several questions will not be answered, but it's due to the time we have. And now we will start the conference. The first and our keynote speaker is Prof.John Hansen from Center of Robust Speech Systems from University of Texas at Dallas. And it's really a privilege and a pleasure to have him with us because he's my friend, and I think a big friend of the speech community. I think that most of the people know this Three Johns book. I have the book from Macmillan, not from IEEE, the Discrete Time Processing of Speech Signals. I think that most of us had the book of Rabiner that was like an Old Testimony. So John's book is like a New Testimony for many of us. John, I cannot tell everything what John did and do now, but let's say that most of his research is very, very interesting, and it's never more of the same. It's always new, always interesting. He's our president, of course, because he's the president of U.S.A, of all the speech community. I can tell that he's also a brilliant professional dancer. I don't know how he has time for this, and we all hope that next time he will not only send his wife to Israel, but will join her and come to visit us. So let us accept John Hansen, and his keynote will be robust diarization in naturalistic audio stream, challenges from multi-speaker and learning spaces.
Itshak, thank you very much. I have my mask that represents kind of the space, and so we'll talk a little bit about that. But thank you very much for that warm welcome. And I thank you, and I thank your university and your center for inviting me and allowing me to participate in this conference and to give a talk here. Understand that in life, you don't go through anything alone. You always have people, friends, and collaborators with you. And I've enjoyed interacting and working with you for many years. And I hope that we can bring interspeech to Israel here in the future. I will say my wife has been to Israel twice. I've not made it there yet, so it's on my list of things that I need to do in life. So I'll make sure that that's my next plan. So let me kind of get started then with my presentation. So the talk here will be on understanding diarization in naturalistic audio streams. So to kind of start with, let's kind of think a little bit about speech processing and where it's come maybe the last 100 years. And so typically people have focused on point-to-point or human-to-human interaction, typically over the telephone network. That's been the primary mode of capturing audio and analyzing speech communication. But perhaps maybe over the last 20 or 30 years, people have seen that it's much more critical not to look just at one-to-one type interaction, but group dynamics. Understanding how people talk and interact collaboratively is actually an important aspect um, in the speech field. Clearly noting here that we're not looking at social distancing, we're looking at physical distancing, but that still implies that we'll have an active and healthy voice interaction amongst multiple people. So the parts here that maybe to think about is first, that audio will include naturalistic data. That means it's not intended to be speech directed just at a microphone or talking one-on-one with someone on a telephone. Secondly, that you'll have multiple speakers, more than 2 or 3 that might be involved in communicating. Another aspect, it would be massive data streams, maybe STEM or educational based context. And clearly today there's more interest and movement in voice enabled type technologies. If you're looking at assistive technologies in the home or in the workplace, this is something that will allow people to stay active in the field. Now, if you're looking at just the topic of diarization, I know many of those of you that are participating today are obviously very active researchers in the field of speech. There may be some that aren't. So I just would like to kind of highlight, what does diarization mean in terms of spoken language technology? So typically what we would do is to focus on first identifying when speech occurs and when there's silence. And once we do that, one might be looking, for example, at extracting the text content. So we could look exactly at the text of what someone is saying. Alternatively, one might want to look simply at the audio or keywords. What are the types of words that might be important for someone analyzing large amounts of data? One could look, for example, at speaker identification and tracking to see who is speaking, what the turn taking is like, and what is the dynamics between the individuals talking. Another might be looking at the topics that someone is speaking about. So if you're looking at those keywords, you might group certain keywords together to kind of associate those with a topic. And finally, you might be looking at the environment. All right, well, I'm glad you jumped in there because let's see here. So this was the first slide set that I had. So here, just showing the, let's see if I do this here. Okay. Here, just showing person-to-person interaction, and then group dynamics, and then some of the key pieces. Then for diarization here, text, keyword, speaker ID and tracking, topic locations, and maybe the environment where someone is speaking would be an area that would be of interest in large data sets for diarization. Next, so I'll talk very briefly about 2 different domains that we've done work on. So roughly for the last maybe 10 or 12 years or so, we've been looking at something called Prof Life Log, and that's where someone would basically record themselves. We use a Lena unit here, which is primarily meant for child speech. Some of our students had worked on some of the development of the technologies for that. And we would wear this, or a person, primarily me being a prof, would wear that for a day. You get about 16 hours of audio in a day. And we would analyze all the communications that took place for that person in a day. So we can kind of analyze different characteristics of that. One might be kind of looking and seeing, well, how much does the person speak versus maybe background silence? What are the types of environments the person is in? So we can kind of look and see where's the person moving based on the acoustics of those environments. So if you're in your office, in the car, maybe eating with students over in the student center and in a dining area, or in a student union, or walking outdoors, we can figure out the amount of time someone is in each of these areas. And when someone is engaged in conversation, how much of the time do you speak versus other people in the group? And determining when they're speaking and how they're speaking is also an important aspect. So one of the things that we developed was a technique to kind of count words in the person's voice. So depending on the types of meetings that I've taken place, we've been recording myself roughly once a month for like the past maybe 8 years. And so we've got quite a few recordings of myself. Some of my students that are in the transcription team sit and listen to me babble on for more than I'm sure they would like to hear. but at least here what we're able to do is to count on different days how much speech is actually produced. So these represent the number of words that I might produce in a given day. So some days are light, maybe 5,000, 23,000, 15,000 words. And some days are much more heavy, 52,000, 53,000, and 57,000 words produced in a day. And it's not maybe surprising that those days might be involved with maybe research or teaching or something along those lines. And if you're a professor at your university, one of the things that you can do is, I think these were recordings when I was department head for electrical engineering. I can go to my dean and say, hey, over these last maybe 8 or 10 days, I spent more time engaging and talking with faculty and faculty meetings, and the next would be student meetings, and then research meetings and teaching. So you can kind of show exactly where your voice characteristics are going. So that would be if you're monitoring one person looking at the communications there. Another might be looking at just analyzing voice dynamics for teaching. So this is another corpus collection we did called peer-led team learning, where students that are grouped together, typically 6 to 8 students working collaboratively together on solving different types of STEM type problems in chemistry, calculus, physics, and so forth. And what we did is, again, collected the audio individually from those students and analyzed how much they were speaking and when they were talking. So this just shows a plot of the automatic system detecting how much time the lead student is speaking and how much time each of the individual students are talking versus human labels. So we're able to kind of do a nice job in characterizing that. Because of the amount of time I have, I won't be able to go into a lot of the details of a number of our algorithms. This is one diarization pipeline we built for that system for peer-led team learning using the SyncNet embeddings. So this shows the convolutional neural network-based systems that build the first stage of a pipeline here, followed by subsequent processing here. And so with this setup, we can achieve some very, very nice performance here for looking at clustering and identification of the speakers that are talking within the system. So next, what I'd like to kind of do is to move more towards larger amounts of audio data that may be made available to the public. So one of the goals in thinking about diarization is how do we access and maybe build a large corpora for naturalistic team-based communications? It's a challenge because privacy issues come to play, and it's something we have to keep in mind. You'd like to also make sure that the audio is meaningful, that there's some type of task involved. So there have been corpora that have been developed where people have gotten together simply to kind of talk about problems in general, but unfortunately they're not motivated or they do not have a specific issue that they're trying to cover. So the ability to kind of collect data like this in a meeting task or multiple people speaking, but also to make it freely available is a real challenge in the field. And one of the reasons that there has not been as much research advancements as we'd like to see over the last few years. The other question that we also think about is what kind of metadata and transcripts are necessary for such a corpus to be available and used by the public. So in terms of collecting, we'd like to make sure that if you're thinking about developing or collecting it yourself, well, typically you might simulate that. There's certainly cost in terms of time, people, and resources there. And also the size and scope of the teams become a challenge. So where might we go to try and get very, very large amounts of data that can be shared with the general public? Well, a number of years ago, we looked and saw that NASA actually collects all types of audio for their missions. And unfortunately, when they collect that data, they simply use it for their own purposes. And there's really no budget or available resources from NASA to do anything with historical preservation. When they collect this audio, they simply just use it themselves and put it on a shelf, and that's it. And one of the next major efforts that NASA is looking at is the Mission to Mars effort. And so that offers some unique challenges in terms of team-based communications and interactions. So one of the goals that we've had is, who funds these types of research activities for naturalistic data? We'd like to kind of build a community-based audio resource that people can get access to. Hopefully people that are speech technologists and scientists like ourselves might benefit from this. One could also expect that educators, small team group, people that study small team groups more in the psychology area. People that are historians or archivists would also find some of the audio here may be of interest. And these are the directions we're kind of looking at. So we're focused here on this particular project that we collected for NASA and where we might move in the next phase of some of our work in this domain. So there are a number of missions. If you looked at the Apollo program consisted of 12 manned missions. Apollo 1, unfortunately with Apollo 1, the 3 astronauts unfortunately perished inside their capsule during an onboard test on the launch pad. And so from Apollo 2 to Apollo 6, those were unmanned, but Apollo 7 through 17 were all manned missions. 7, 8, 9, and 10 were all critical in setting the stage for Apollo 11 that allowed man to go to the moon. Apollo 12 also made it to the moon. Apollo 13, unfortunately, had a major catastrophe or accident with respect to some oxygen support tanks that did not allow Apollo 13 to land. But it actually represents one of the greatest engineering challenges that NASA had to overcome to ensure the safe return of the astronauts. Apollo 14 through 17 also were manned missions and included lunar walks and other aspects on the moon. So more recently, over the last few years, the International Space Station has housed a number of international researchers and astronauts. Typically 6 are on board at any one time, and they have live communications between Earth and the International Space Station. Long-term type interactions there are important. Another thing that actually we may not have thought about here the last maybe 6 months ago, but NASA has had what's called a HERA, that's the Human Analog Research Program, that's been an ongoing effort for more than 10 years. And maybe any of you listening to this talk might decide you might want to participate in that. These are basically long-term type confinements in closed quarters. And so a system or a living space like this would be something where maybe 4 people would go into and be housed there from anywhere from 1 week to maybe a year. And one would perform different types of experiments inside and look at the human dynamics of how people interact and accomplish team projects. And so this is something that NASA finds important because it's one thing if you're going to go to the moon, that's typically a 6 to 10 day type mission. It's another thing if you're going to go to Mars and it's going to take you 3 years to get there and back. So long deep space type missions require a lot more knowledge and understanding of human interaction and team-based accomplishing of these tasks. So the project we originally had funded by the National Science Foundation looked at trying to develop a strategy to first collect that audio, do some type of high technology labeling of that data, connect content in terms of speech, images, video, and content, so forth, along this timeline. And so this was our goal in 2012. We decided to focus on Apollo 11. So Apollo 11 as a mission was 8 days in length, from launch through orbit to the moon, landing on the moon, walking on the moon, and returning. Seems like a nice, easy task, but unfortunately today, well, at the time, you got to realize in 1969, we didn't have cell phones. And so just the ability to figure out how to actually talk to the moon, how to actually capture both video, images, and data back and forth to the spaceship was never attempted by anyone yet. So there was a lot of major engineering challenges that had to be overcome. In terms of developing or achieving the mission, NASA had come up with a system or a support team that would allow this to happen. So this is referred to as Mission Control Operations Center. So MOCR is basically this room that you see here, large numbers of people sitting there that are responsible for each of the different phases of the mission. They're referred to as flight controllers that are responsible for things. These individuals then would talk collaboratively on an audio system. The audio system was a 30-track recording system. You can see down here in the lower left hand. And in terms of the communications, you'd have one lead person, that's the flight director, who controls everything, and one individual that's allowed to talk to the astronauts. That person is called CAPCOM, or capsule communicator. That's the only person that's allowed to talk to the astronauts. clearly, you have launch, you have the ability to monitor the transmissions and all of the movement going forward. So keep in mind that this is an 8-day mission, so no one individual can stay awake for 8 days straight. And so NASA had multiple teams. The white team, led by Gene Kranz, who was flight director, was kind of the lead team that oversaw most of the key phases of the mission. There was the green team, the white team, and the black team as well. And each of these were responsible for different phases. Primarily green, white, and black were the three teams that would basically alternate. So they were basically on for 8 hours, and then the next team would come on for the following 8 hours. Each mission controller would typically overlap by an hour to ensure there was a nice handoff, if you will, to the next team. And so these represent some of the flight controllers, the three flight controllers that were actually responsible during Apollo 11. If you wanted to see one of the teams, this is the white team headed by Gene Kranz, who's sitting right here. Interestingly enough, the person next to him is Capcom. His name is Charlie Duke. And an interesting thing that Charlie Duke was Capcom for Apollo 11, but he was also an Apollo astronaut and walked on the moon for Apollo 16. So it was quite common that NASA would use future Apollo astronauts to actually be capsule communicators because they had gone through the same training that the astronauts had gone through. So in looking at the data, this is actually mission control. Interestingly enough, there's actually two mission controls. This is the mission control operations room that's in Houston, Texas, or the Johnson Space Center. It turns out that during launch in the United States, we launch rockets from Kennedy Space Center, which is in Florida. They also have a control room, but that control room is only responsible for launch and the 10 minutes after launch. After that, all operations and control goes to Houston here for this room. Now, I mentioned that there was a system that actually recorded all the audio, and this is one of the units, which is a playback unit. That system actually allowed you to record 30 different channels, and these were referred to as loops. There was typically 3 to as many as 33 people speaking on each of those loops, and it was critical to kind of capture all the audio. This gentleman here is Greg Weisman. Greg is head of the communications lab for NASA, and he's actually playing back one of these tapes. This is a system called SoundScriber, and this is a playback option for SoundScriber. You'll notice that he has a very high-tech solution here to try and maintain the proper tape tension on the tape here. And that high-tech solution is this little yellow bungee cord. If you've ever taken a family trip and put luggage on your roof, that's the same bungee cord that you might use to put luggage on your roof. He's using that to maintain the right tension on the tape in order to try and make sure he can play it back. So we had some challenges when we got our first NSF project here. We went to NASA. We had assumed that they had digitized all of this, and they took us into a back room and showed us boxes and racks of tapes and said, well, all the tapes are there. There's the SoundScriber system, do what you need to do. And we asked, well, we thought you had digitized this. And they said, no, we haven't digitized anything. If you want to, you can try digitizing it yourself. Unfortunately, it turns out that the read head on this only reads off one track at a time. Each of these tapes is actually 14 hours in length. And unfortunately, it would take roughly a month to digitize that one tape. At that rate, it would take about 172 years to actually digitize all of Apollo. So we felt this was not an option, okay? So at this moment here, I'm gonna pause and maybe not share the screen for a moment. I think if I can do this here, maybe I can't. I don't know if I can do this here. Maybe I'll wait until afterwards. I do have actually one of the tapes with me here, so maybe when we get into the question and answer phase, I'll show that at that time, okay? So I'm gonna move along here because I've got a few other things to try and cover. So in the corpus development here, we went through, spent roughly about 6 to 7 years working on this. It took us almost a year to digitize and process this data. This is one of the tapes that was actually the physical moon landing. One of our students who spent 4 months there digitizing tapes and going through the audio process there. It was a long, tedious type effort. In the setup here, for us to actually come up with a solution to digitize this, we had to actually remove this single track head and build a 30-track read head that we could actually use to digitize all 30 tracks at the same time. Once I designed and built that, I went down to Houston expecting NASA to have some great engineers to help me. And they said, you know, if you need to install it, do it yourself. So I did. And it was pretty scary because if we messed it up, we would probably hop in a car and drive to Mexico because that's the only playback system there is. And if we broke it, no one's going to be able to listen to those tapes. So I'm going to play one of the audio clips here you can hear.
The decom was taking input from receiver from this rolling right 40 degrees to roll 122, pitch 229, yaw 0, over.
Okay, so you can hear that there's multiple people on there. Each channel, you kind of refer to it as a loop. These represent different recording conditions that are in there. This kind of shows that you have the astronauts in space. This is the mission control room. One of the unique things behind each of these individual seats is a backroom support staff. And this staff support backroom team actually provides the interaction and knowledge that the flight controller needs to make their decisions on where things are going to be going in the next phase. So in setting up our setup, we had obviously the communications. One would see you'd have the CAPCOM, capsule communicator, talking to the astronauts. CAPCOM talks to the flight director talks to all the flight controllers, and behind each of the flight controllers are typically backroom support staff, each in different locations that are sent to support the flight controllers. Another small thing that you have to remember is that when you talk to the moon, you don't necessarily have a line of sight between Earth and the moon, or at least between Houston and the moon. So there's typically 6 or 7 relay stations across the globe, one at Goldstone in California, one in Madrid, Spain, one in Canary Islands, one in Australia and elsewhere. And so if the communications was coming from the rocket where it could not go directly back to Houston, it got routed to one of these other listening stations and then routed back to Houston. So there's another hop that went in there. But the diarization pipeline, you can see here, we do speaker tagging, diarization for speaker tracking, full speech recognition, diarization, and we generate other types of tasks that come off of this. In order to do the speech recognition, clearly NASA speaks in a non-typical lexicon, so to speak. And so we had to come up with a way to find all the words and phrases that NASA might use for the different missions. And so we captured about 4.2 billion words from different text corpora. These are books, reports, all kinds of NASA mission reports from both Apollo, Gemini, and International Space Station, and sources. And we used that to build a language model as well as the lexicon that could be used for this task. And so our processing pipeline allows us to kind of now generate a full text transcription of everything that was spoken on each of the channels. Once you have this, you can now come up with interesting analyses of the audio in there. So this figure is referred to as a chord diagram, and it represents, if you've got a number of people sitting around a table, who is speaking and how much of the time they're talking. So in this blue section here, this represents the capsule communicator and how much time he might be speaking. The links here kind of show how much time this individual is speaking to this other person. Here it's Buzz Aldrin, Neil Armstrong, and Michael Collins, the 3 astronauts from Apollo 11. I'm going to play one of the examples. You can't listen to this talk without kind of hearing at least this speech.
At the foot of the ladder, the lamp footbeds are only depressed in the surface about 1 or 2 inches, although the surface appears to be very, very.
Somehow, I guess it just stopped. But that's the one small step for man, one giant leap for mankind. In addition, you also hear sometimes the astronauts saying some interesting things. So we did actually catch Buzz Aldrin kind of talking to NASA, and he is kind of complaining because when he looks out the window at Earth, all he sees is ocean, and he's not so happy about that. So listen to what he's asking NASA to do.
Hey, Houston, you suppose you could turn the Earth a little bit so we could get a little bit more than just water? Roger, 11. I don't think we got much control over that. Looks like you'll have to settle for the water.
So Buzz was asking if they could turn the Earth so he could see more land, and NASA said they can't do that. So the other parts you look at here, we can obviously characterize conversational word counts, other aspects there in the communications. These all allow us to kind of analyze the different traits which are important. One of the things that we also looked at is we looked at the sentiment of the audio from the astronauts. So this shows things were quite positive for most of the time. There were a couple of negative sentiment phases in there. But you can see they were all quite positive. There's some levels of stress when they're landing and taking off. Imagine what this might look like for Apollo 13, which obviously was under much, much more stress. More recently, we've also been looking at an effort called Finding Aldo. And when we originally released this audio, we found a number of people came back to us and said, hey, my uncle, my grandfather, my dad ended up working at NASA. You know, do you have some examples of his voice? And so we said, well, let's go ahead and see if we can find any individual that's talking in the Apollo missions and see if we can kind of pull them aside and actually set up a separate web page or connection just for that individual and all the audio they would produce. So try and have some type of a lasting memory of each individual that might have contributed. So if you look at this mission control, you can see it's much larger than the one I showed you earlier. This is the one in Florida for launch. One of the individuals I indicated here was Charlie Duke, who was a moonwalker for Apollo 16, and this is what Charlie looks like today. He actually visited UT Dallas about a year and a half ago for a talk with some of our students. So in Finding Waldo, we can find individual speakers here, Charlie Duke, Gene Krantz. So I'll play one of them.
For Neil, based on consumables and all parameters, we can give him another 15 minutes and still give a minus 10-minute mark for Buzz to start termination if he concurs.
Okay, so in these things, you can kind of see that we can identify the individual speakers and allow them to kind of pull things together. For time purposes here, I'm going to move on. One of the things that we've done is we've released this full corpus for the community. There's a smaller challenge corpus that we drew from the 19,000 hours that we pulled out. For Apollo 11, it's about 11,000 hours. Apollo 13, we've got about 8,000 hours for that one. We pulled about 100 hours out from liftoff, landing, and lunar walk, and that represents the Fearless Steps Challenge that we released in 2018. 155 different organizations from 35 different countries have participated in that. And we've been using that to share different challenge competitions for different tasks. These include speech activity detection, speaker diarization, speaker ID, speech recognition, sentiment assessment. And this was done in 2018 as well as 2019 as well. This shows kind of the map of different continents and which organizations have accessed the corpus. So if you'd like to get access to this data, I'll share obviously these slides. But you can freely download at least the full 100-hour corpus. If you want to pull down the full Apollo 11 corpus, that's 11,000 hours. Feel free to do that. We're providing the audio, all of the transcripts, a search strategy system within an Excel file, plus the language model and the lexicon that we use to build the diarization pipeline for our system. So all of that is freely available that we pass out. I'll kind of close here with a couple more comments. First, we've been in the news. We've had close to about 35 to 40 TV, radio, newspaper interviews. NASA has done a 4-part podcast on the efforts that we've put forth here the last maybe 8 years, and I can provide links for that. One of the things that was particularly memorable for our students and our team was that CNN came to us before 2019 because they wanted to put together a documentary on Apollo 11. And they had some challenges there. And the reason was because NASA had recorded a lot of the video of everything that was going on in mission control. But unfortunately, it was all silent 70mm video. And so I'll show you some of that video here in a moment. But in order to put audio with their silent video, we passed all of our diarization transcripts, all the organized audio, and all of our audio was used and stitched together in order to put a voice to the movie for Apollo 11 that was broadcast here in the U.S. and on TV 3 times in 2019. So here's Charlie Duke and Clifford Charlesworth, who are 2 of the flight directors here in Gene Kranz. So what was happening is we'd have silent video. So I'm going to show you, this is the video here, and there's no audio there. You can basically see that Charlie Duke's just talking. And if you can believe this, what the movie studio was doing was trying to read the lips of this individual and trying to guess what he said, and then asking NASA, hey, could you find that audio for us? And NASA said, no, we can't do that, but we can, direct you to Hansen up in Dallas, and he might be able to help you. So this is what came out of that. So you can see the video there kind of drops in and out. It's not because we've got a bad connection. It's because the video was only recorded from a handheld camera that a videographer walked around there. You notice that the audio here could not have been recorded on that video camera, because if it was, you would only hear what the person you see is saying. You won't hear what that person is listening to. So because you're hearing both sides of the conversation, you had to have gotten the audio from internally in the internal communications. So other examples, here's another one with flight director.
Capcom flight. Good flight. No response necessary, but we're in good shape on consumables on CDR.
So consumables, CDR represents commander. He's talking about Neil Armstrong, and consumables are core things like oxygen. You need that, and other things that in order to stay alive there. So they're monitoring that through through one of the flight controllers that monitor electrical and consumable type units. This is another example here.
Start flight, Roger. That's all engines, Roger. Clear the tower, Roger tower. Roger, we got a roll program. Flight pilotability IP. Roger, IP.
Okay, so shows you some examples there of how we can stitch things. If you're interested, you can go to this website. This is set up by a number of our undergraduate students over the years, and we've pulled in a number of different audio clips there during the question and answer phase. I might play one of those if we have a little time. In addition to that, one of the questions is kind of preserving this. We got all of Apollo 11. For Apollo 13, unfortunately, there were 4 tapes that were missing from the NASA archives, and so we only got a portion of Apollo 13. But the rest of those Apollo missions are still there, and they're all sitting on these analog tapes. And so the question was, well, what's going to happen with these tapes? Because they're over 50 years old. And so, we felt it was really important to try to recover all those audios. And so we submitted a proposal to the National Science Foundation last year. They asked us to go through and have a series of workshops, which we've done over the last 8 months to try and capture feedback from the community. And last week, we learned that NSF is awarding us this project. The follow-on project will start September 1st, 3-year project, $1.2 million, to go back and actually recover the remaining portion of all the Apollo audio. So this will now produce the largest task-based audio corpus that will be freely available to all the community, speech community, as well as history and archiving individuals. A collection of 150,000 hours of audio will be made available, along with full transcripts for all of that data, so people can kind of analyze and develop new strategies there. So that's going to be coming online. If you've got interest in this, please let us know. We're happy to share all the data. Downloading 150,000 hours is not an easy task. So we've partnered with the Linguistics Data Consortium, LDC, to help us with the distribution of this. So I'll close by first thanking Itshak and your university for allowing me to give this talk. I'd like to recognize and thank all the individuals we've interacted with at NASA, in particular John Stahl and Greg Weisman. Greg has been one of the strongest supporters of our efforts here, freely gave his time and allowed us to have access to all the equipment and all the infrastructure there. Doug Ord, one of our collaborators from the University of Maryland, who is an archivist and just a world-class expert on Apollo, just a really great collaborator and friend to work with. And in particular, I'd like to recognize Tanya Kurelski and the U.S. National Science Foundation. They saw the need and benefit of recovering an audio corpus of this size, both previously and the next steps here. So we really thank NSF and Tanya Kurelski for their support of this effort. So I'll pause now and ask for questions.
Thank you very much, John, for a very interesting talk. Here we also love to talk, but less like to write. So I don't see questions. Maybe because we love to talk. Oh, this is the tape.
So this is one of the tapes. You can see there's something called a heat sheet on here. These are each of the 30 different positions that the recording would be taking place on. And this is actually the tape. This was one of the tapes we actually captured from Gemini, Gemini 8. And the reason why Gemini 8 was important was because that was the mission that Neil Armstrong was commander on. And so we had that one beforehand. I'll also show you, this is actually set up here. So when you're flying to the moon, you don't have ways to figure out where you're going. So for Apollo 11 here, they had to have maps that would actually show you where you're actually flying on the moon. So they had to study these maps to kind of figure out where they needed to land. And those were all one of the challenges that the astronauts had to face. And the last little thing I had, so these are all original. We were fortunate enough to have one of the people that worked at NASA to share that with me. These are just on loan. I don't own them. And then the other part is that if you're working in mission control, you've got a lot of things that you got to remember. And, if you're a professor, probably, your students might have a study guide or something called a cheat sheet. And this is an actual study guide or an event thing that every flight controller had. And it basically told them exactly what was going to happen and when it was supposed to happen. So this way they can keep track of what was going on during the mission. So I'll stop and ask if there's any questions that folks might have.
Okay, John, thank you very much for the talk. I have two very short, quick questions. First of all, when you do diarization, I see you work on all the data together. Can you first to separate the bunch of speakers due to the channels? These are the aircraft and these are at Houston, or you do all the process all together?
So what we do is when we digitize the audio, we break up the audio into 30-minute chunks. Each of those chunks would have a separate channel. So when we digitize, we actually pull all 30 channels together, but we have each of those channels separated. So the nice thing there is that we do diarization on each channel separately and for a 30-minute block. One of the things that also happens is that obviously this is analog. So I could show you examples of all of the cabling that had to run in order to get the headsets and the handsets and everything for each of the flight directors. And so there's lots of background noise and other factors going on in mission control, but we process each of those channels separately. We first look at speech activity detection, then we look at speaker clustering for speaker A, B, and C, how many speakers are there. And then once we have that, then we go through and do the speech recognition and associate the text with each of the speakers. Now, we do actually have their names, but what we've been using is just their handle. So if you're the flight director, we might say FD1, FD2, FD3 for the 3 different flight directors. If your PAO is the public affairs officer, so we'd have 3 different public affairs officers depending on the type or the time of day that the person might be speaking.
Thank you very much. Because we are short on time, we'll go to the next talk. And thank you again from all of us.
Thank you.
Our next speaker is Dr. Deborah Cohen from Google Research in Israel. She did her BSc and PhD at Technion, and she won a lot of prizes and awards, so I won't list them all, just to say that it's a lot. And currently she's a senior researcher at Google, and she works on machine learning and NLP. Her interests are basically signal processing, compressed sensing, reinforcement learning, and conversational bots. And let's invite Deborah for her talk, dynamic composition from domain exploration dialogues.
Hello, everyone. Thank you, Itshak, very much for the introduction. My name is Deborah, and I'll present today the work from my team at Google Research in Tel Aviv on conversational domain exploration. So a short disclaimer, this talk is very loosely connected to speech. It's more have a flavor of conversational AI and NLP. And this was presented at the web conference from what was supposed to be Taiwan and ended up being my living room. So when we look at the spectrum and conversational AI bots, we can see on the one side bots that aim at helping users to fulfill some tasks, such as making a restaurant reservation or getting some answers on a specific domain or getting a recommendation for a movie, for example. And on the other side of the spectrum, you have these social chatbots that are very engaging, but are not grounded in domain. So in some domain knowledge. So what we propose to look at is what we call domain exploration. So this is for the use case where a user would want to enrich their knowledge about a certain domain, but do so in some kind of engaging conversational experience. So we need to be grounded in domain knowledge like the task-based bot, but we also need to be engaging like the social chatbots. And starting from the end, this is a real conversation done by a user using Google Assistant and talking with our bot, specifically on NBA. You see here that the user started to ask about the Last Warriors game. And we answered that question with the score, and then we added some kind of enrichment in the form of a teaser. We said that Curry was the top scorer without saying actually how many points he scored. And the user was interested in that information, so he asked for it, and then we provided it and added some additional stats about Steph Curry. Then the user moved on to talk about the next Warriors game. And we replied to the query and added some additional interesting facts. So this is an example of a real NBA conversation. If we move on to another domain, here's an example of a conversation about animals. So the user started talking about penguins. We kept the engagement in the conversation by asking the user a question. And then at some point, we changed the focus from penguins to emperor penguins, a subspecies. And then something you can see that is common to this conversation and the one from the previous slide is that the bot responses are composite. So instead of simply answering the user query and get some kind of Q&A experience, we provide additional enriching fact. we kind of drive the conversation. The bot is proactive in driving the conversation by asking questions, changing the focus, and so on. So how does it work? We called it dynamic composition, and it works like this. So let's take a high-level look of the architecture, and then we can deep dive into each component. So the first thing that we do when we get the user query is that we do some user input analysis, some NLU, to better understand what the query is about, what the user intent is, and what the entities, what are the entities that the user is talking about. Once we did that analysis, we turned to our content providers, which suggest different candidate responses to that query, depending on their domain of expertise. So we have content providers that extract facts from the knowledge graph. We have content providers that extract facts from the web. Content providers are able to ask questions, to make some comparison between different entities, to change the focus like we saw, et cetera, et cetera. So at that point, we end up with several candidates that can be potential responses to the query. We turn to the dialog manager, which is the core machine learning model in the system. And the dialog manager basically scores each of these candidates and picks the best one. Now, we saw that the bot response is composite. So we kind of do this process in a composition loop. So once the dialog manager picked a response, we go back to the content provider and ask them if they have something to add. And then the content provider, again, offer different candidates. And then the dialog manager, again, will score them and pick one. All of this in the composition loop until the dialog manager decides to end the turn. Now we end up with a few sentences coming from different sources, different provider, that we kind of need to stitch together, because just concatenated these sentences would be very clunky. And this is what the sentence fusion is doing, kind of fusing the sentences together, changing the text if needed so that the flow is better. And here you see an example of the response that we provided to the user, composed of two responses. The first one coming from the knowledge graph, and the second one being some insight fact about the first one. Now, if we change the domain and move from animals back to NBA, the only thing that is going to change is the content. So we get the same technology, we get the same architecture, but we only need to change the content. Instead of talking about animals, we'll talk about NBA players and team. So we keep the same technology of knowledge graph extraction and comparison and so on, but we change the entities that we're talking about. So just to kind of situate our approach into the different approaches in the literature. So there are several dialog approaches, including the scripted approach, which is typically of high quality, but very hard to scale. We have end-to-end generative approach, which are very flexible, but the quality is very hard to control, and these are seldom used in industry for that reason. And then we have retrieval approach, which are kind of bound to the initial index that we're building from, and don't have the flexibility to provide different answers to different dialogue context. So what we propose is kind of in between, what we call the dynamic composition, where on the one hand, we have the content providers that we can control. So we can control the fact that the content that we provide is exact. And on the other hand, we have this flexible model that mix and match different sentences together, and we have the flexibility to compose response like this. So let's dive into the different components of this codex box for conversational domain exploration. And let's start with the first one. So user input analysis, or basically NLU, is composed of several modules, and the most interesting one is the focus tracking. So focus tracking focuses model as a bag of entities, and it kind of tracking the focus kind of builds a thread into the different entities that the conversation is about. So in this example, we have penguins, moving to emperor penguins, moving to little penguins. And we also distinguish between primary and secondary focus, where in the last bot response here, the primary focus would be the little penguins, and then the secondary focus would be their weight. And this enables us smooth transitions and compositionality, because we can move from different entities whether they are the primary focus, like the animal here, or the secondary focus, like their property. The model that we use for the focus tracking is composed of an LSTM running over the last user input. And at the end, we get some kind of sentence embeddings of that input. We also take into account different candidates, different pairs of primary and secondary focus, extracted from all the entities in the conversation, as well as related entities. And then we do some softmax over the candidates. Next, we move on to the content providers. So these are the building blocks for the bot responses. Each content provider can offer one or more candidates as a response to the user query, given the context of the conversation. Each provider uses a different source and a different technology. So for example, we have a knowledge graph provider that is performing knowledge graph mining of facts from the knowledge graph. We have some unstructured text provider that perform either generative summarization from, let's say, news article, or retrieval from as fun facts from the web. So you see here in green an example of the KG, the knowledge graph provider, and in purple an example of a fun fact from some unstructured provider. And besides these purely informative providers, we have what we call the conversational drivers, whose goal is to have the conversation more engaging. So we distinguish between three main conversational drivers: questions, so asking when the bot asks the user to ask a question, and that breaks the kind of Q&A pattern. Topic changes that can be in the form of a question or a comparison, for example, between two entities. And teasers, where the information is formulated in a way that we don't reveal the whole fact, and an engaged user can ask for a follow-up question, like we've seen earlier in the NBA conversation. Okay, so at that point we have maybe a few dozen candidates, and we need to pick from them. And this is the role of the dialogue manager. So how does it work? Assuming that this is the conversation that we have, and the user said something like, actually, I'd like to hear about little penguins. So we go to the content provider, and assuming that this is what they offer, the dialogue manager will score each, and then pick the one with the highest score, assuming that's the first one here in green. Then we go back to the content provider and ask them if they have something to add, given that we already are going to answer this first fact. And this is assuming that this is what the content provider will add. We pick after scoring, we pick another fact. And then let's assume that at that point, the dialogue manager decides to end the turn. We end up with that response, composed of two facts selected by the dialogue manager. So you can see here that the response is a bit clunky. We repeat twice little penguins. This will be taken care of in the last module called the sentence fusion. Okay, so let's talk a bit about the dialogue manager. Let's start with the training data and then move on to the model. So we have a few crowdsourced human evaluators that generate the conversation and then evaluate the bot responses. For each domain, we have something like 1.5 conversations, leading to 150K training examples, where the rating is done on a scale from -3 to 7. The interface of the dialogue manager is as input the conversation history as well as a candidate, and then we output a score and the state for the next turn. And here's how the model looks like. We have an RNN encoding the state of the conversation, getting as input some representation of the user input, the bot reply, and then the candidate, as well as additional metadata feature, which I'm going to skip due to time limitation. Once we have scored all the candidates, we can use different policies. We can be greedy and pick the one with the highest score. We can do beam search within the turn. We can do exploration. And we're now looking at using reinforcement learning to optimize not only the next response, but the whole conversation. Okay, the last module is the sentence fusion, which kind of fuse together independent sentences into some kind of coherent response. So here you see on the right, two sentences coming from different providers. what the sentence fusion does, and we have a rule-based model right now, is 3 things. We do pronominalization, adding discourse markers, and remove the context. And here's how it looks like in this example. So we removed the second James Harden, we removed the second in the game, and then we added a connector. We are also working on a machine learned version, and you can try to look for our DiscoFuse paper. Okay, and I'll just end up with some results from the live experiment that we run. So on the right, you see what the vanilla assistant would answer a user talking about NBA. On the left, you see our bot. And the experiment, the experiment was run so that a percentage of the user will get our version, so the version of the left, instead of the vanilla assistant without knowing it. And we try to measure user engagement. And to do so, we measured a few metrics comparing experiment and control. So here are the results. We have an increase in NBA queries. We see also an increase in follow-up rate, where follow-up is the number of queries, of immediate queries coming after the last user query. Specifically, an increase in NBA and other sports follow-up rate. We also see an increase in explicit positive feedback, such as thank you, but also an increase in negative explicit feedback, meaning that some of the users didn't like the experience. And that depends on the user itself and also on the situation the user is in that is maybe not inclined to have a conversation right now. So some additional insights from the experiment. We saw that the type of the device is very important. We saw higher engagement in devices with screen, a lot more sensitivity in voice-only devices. So when the user is interacting only with its voice, specifically with respect to the length of the bot response, and also most of the explicit feedback, both positive and negative, was in voice-only devices. We also saw the impact of the conversational drivers. So adding teasers, focus changers, and questions really increased the follow-up rate and made the conversation more engaging. And to conclude, a few challenges that we're working on right now. So first, we're working on learning from real user conversation rather than raters, which are unlabeled. As discussed before, we're working on reinforcement learning, and then we're trying to come up with some evaluation paradigm for that kind of conversational domain exploration, where there's no clear intent into what the user wants to achieve. Thank you very much.
Thank you, Deborah, for the interesting talk. Because we are running out of time, we will go to the next talk. Okay, before we will go to our next talk, I will say again, if you want me to ask in your name questions, please text me and I will read the questions. Our next speaker is Elia Nachmani. He's from Tel Aviv University and from Facebook. He did his BSc at Technion and Masters at Tel Aviv University, and he is currently a PhD student at Tel Aviv University. And in parallel, he works at Facebook AI research. His interests are deep learning, signal processing, and information theory. His talk will be about single-channel speech separation from unknown number of speakers.
Hi everyone. So today I'm going to talk about voice separation with an unknown number of multiple speakers. This is a joint work with U.S.A and Lior Wolf from Facebook AI Research and Tel Aviv University. This talk also going to be presented at ICML this year. Okay, so this is the outline of the talk. At the beginning, I'm going to talk about the problem setting and prior works. And then I will talk about our model and our new loss terms. And then we will see which dataset we use and the result of our model. And then we will show how we can move from known number of speakers to unknown number of multiple speakers. And then we will show how we can improve the result with test time augmentation, and then our summary. Okay. So the problem setting is that we have multiple speakers that talk simultaneously, and we want to separate them. We have single microphones that record them, and we want to do a blind source separation and to get each one of them. For example, we can hear a mix of 3 people that are talking.
The NASD released short interest figures for the first time November 25th for all stocks later this week for as many as 40 million shares.
And we want to get each one of them.
It also owns 3 state business magazines in Florida, Georgia, and Arizona, period.
So this was the first one. This is the second one.
The NASD released short interest figures for the first time November 25th for all stocks carried on its NASDAQ automated quotation system.
And this is the third one.
The company said it would begin a double quote Dutch auction double quote later this week for as many as 40 million shares.
Okay. So our goal is to estimate C different input source, Sj, given a source signal that we call X, which is a linear combination of Si. This is a fully supervised case when we have tuples of the input mixture X and the ground truth is S1 to Sc. And we don't have a speaker identity. Okay. So Perrier works. Traditionally, signal processing techniques were applied to this task. For example, winning filtering, MVDR, and independent vector analysis. Recently, deep learning approaches were applied to this task. For example, TASNet, which use an LSTM network to separate a single channel speech. And then was the ConvTASNet, which transferred the LSTM into a convolutional neural networks and get an improvement. And then we have the dual path RNN, which we call the DPRNN, which efficiently take log sequences and model them. Okay, so the architecture of the Perrier works was we have a mixture of speech signals at the input. We have some encoders. The encoder gives some latent representation. This latent representation go to a separation model. The separation model given a masking. The masking multiply the output of the encoder. And then we have the decoder that output the separated waveforms. Okay. So our model uses at the beginning an encoder E, which you get at the input the mixture of the speakers and output a latent representation that we call Z. We use the 1D convolutional networks with the kernel size L. We take the latent representation Z and divide it into R overlapping chunks of length K, and we have the tensor V. We take V and we fed it into a separation network Q, which has BRNN blocks, and the odd blocks are applied along the time dimensions, and the even block are applied to the chunking dimension. Next, we apply a 1-by-1 convolutional layer and to produce C output channels. And lastly, we apply overlap and end methods to output the waveforms. So the architecture looks like this. We have the mixed input. We apply the encoder, and then we have the chunking. We get the V-tensor, and then we apply the Mullen cut blocks. And after that, we have the decoder and the overlap and end, and we get the separated signals. We can see that we can apply the decoder and the overlap and end after each one of the block. In this way, we can apply our loss term after each one of the block and get a better gradient flow. Okay, so the Mullen cut blocks is 2 separated LSTM networks, M1 and M2. We take the input tensor V and apply M1 and M2 and do an element-wise multiplication. And then we concat V and apply a linear projection PI. We also apply a skip connection after each one of the blocks. Okay, so our objective terms is the first one is we want to minimize the scaling variant signal to noise ratio, which called SISNR. Basically, this is a 10 log 10 of the second norm of the signal divided by the noise, where the signal is basically a normalized correlation of the network output and the ground truth. We also apply permutation and variation loss. Basically, we try all the possible permutation at the output of the speakers and choose the best permutation. And for this permutation, we apply the SISNR loss. As we see earlier, we can also apply the multi-loss, basically, which means that after each block, we can apply the loss. The second objective term is perceptual loss. That we have some auxiliary networks G that output a speaker embedding. And we also have the STFT operation F. So we take the output of the network as J and apply the STFT and then get the speaker embedding. And we want that to be as close as possible to the speaker embedding of the ground truth. Basically, this perceptual loss make the output of the speaker consistent. So this is the model block. We can see our model here. It, for example, output 2 speakers. We move it to the permutation invariant loss with the ground truth. The permutation invariant loss also output the optimal permutation to the ID loss, which you get the output of our model and the ground truth. Okay. So in order to evaluate our method, we use the Wall Street Journal 2 mix dataset and Wall Street Journal 3 mix datasets. We also use WAM and WAM-R dataset, which is noisy and reverberation datasets. We also expand these datasets to 4 and 5 speakers, Wall Street Journal 4 mix and Wall Street Journal 5 mix. The creation scripts can be found in our website. Okay, so all the result of our model, as we will see, it is the SISNRI, which is a scale invariant signal to noise ratio improvement. We can see here for Wall Street Journal dataset, which is a clean dataset, the result for multiple speakers from 2 speakers to 5 speakers. We can see here, for example, that for 3 to 5 speakers, we get an improvement for almost 2 dBs over the previous state-of-the-art methods. And for 2 speakers, we get an improvement of over 1 dBs. So let's hear an example of how we separate 4 speakers. So this is the mixed input.
In New York Stock Exchange, New York, traded Friday, 6.8%. Company stock closed at 23.
This is the first output.
Constant Partners of New York said it has a 6.8% stake in Gillette and may seek.
This is the second output.
In New York Stock Exchange Composite Trading Friday, the company stock closed at 23.
This is the third output.
Sales in stores open more than 1 year increased 6.7%, $10.5 million.
And this is the fourth output.
Increasingly, people who test positive join the support groups that have sprung up across the country in the past year, period.
Okay, so we also run an ablation analysis to see which component of our model give the improvement. We can see at the bottom our complete methods. We can see that if we remove the ID loss, we get a degradation of, for example, 0.3 dBs. If we remove the multi-loss part, we see a greater degradation of almost 3 dBs. And if we remove the gating part, we can see a degradation of 2 dBs. We also test the effective of the ID loss. We can see that what is the percentage of the switch between speakers in the same output channels. We can see that if we apply our ID loss, we get an improvement of 2%. Here we can see the result for the WAM and the WAM-R dataset. We can see, for example, for WAM dataset, we get an improvement of almost 2 dBs, which is a noisy dataset, and for WAM-R dataset, we get also the same improvement over the previous state-of-the-art methods. Let's see some example. This is the mixture of WAM dataset.
But on October 31st, there were press reports that coal.
This is the first output.
But on October 31st, there were press reports.
This is the second output.
Reports that coal.
The diversified utility provides gas and electric service.
Okay, and for WAM-R, this is the input mix.
The enormous amounts of carbon dioxide in the atmosphere caused this high pressure.
This is the first output.
The enormous amounts of carbon dioxide in the atmosphere caused this high pressure.
And this is the second output.
But excluding fuel and food, the index probably rose 0.4% or 0.
Okay. So now let's see how we can move from a known number of speakers to unknown number of speakers. Let's see what happens if we feed a mixture of 2 speakers in a recording into a 5-speaker separation model. So this is the mixed input.
Recognition
but on October 31st, there were press reports that Kohlberg wouldn't increase its offer, and rumors that the bid might be withdrawn.
Federal government sales.
This is the first output. So we can hear that this is a noise and silence. This is the second output.
There were
also noise and silence. This is the third output. Also noise and silence. This is the fourth output.
But on October 31st, there were press reports that Kohlberg wouldn't increase its offer, and rumors that the bid might be withdrawn. Period.
This is the first speaker, and this is the 5 output.
Recognition said it reorganized its U.S. business into 3 units: sales and service, federal government sales,
which is a clean speaker. So our method is to start a model with the largest number of speakers, and then we compute the mean of the signal power of each output source. And in this way, we detect the number of the non-active channels, J, and then we repeat with model of C-managed gel output channels. We continue to do that until we didn't detect any silence or we reach to 2 speakers model. Here we can see the result of the methods. For example, we can see at the bottom the oracle, and in this line we can see the degradation with our methods. We can also see in the diagonal the accuracy of detecting the right amount of speakers. Okay, so test time augmentation. We saw that if we start the separation at different points in time, it yields different results. So we propose an augmentation by doing a cyclic quotation of the signal using a random location, and then we average the output. So for example, if we have this signal, we by random choose this point and feed into the model this signal, and then we average over various inputs. We can see here the results. For example, we can see for 5 speakers, our model without augmentation get a result of 10.56 dB, and with 20 times augmentation, we get a result of 10.93 dBs. Okay, so for summary, we introduced a new model architecture for speech separation. We saw that multi-loss improved the optimization due to the masking-free model. We also saw a novel ID loss that maintaining the speaker in each output channels. We also introduced a new dataset for 4 and 5 speakers. we see that our model achieves state-of-the-art results for 2 to 5 speakers. We also saw that our model works good in noise and reverberation environments. And we propose simple and effective methods for model selection to support multiple unknown number of speakers. And lastly, we propose a test time augmentation to improve robustness to the starting point. Thank you.
Thank you very much. I have one short question. What would happen if you assume that the maximum number of speakers is 3 and actually there would be 4?
So for what we saw, that you get in 2 outputs 2 clean speakers, and in the third one you get a mix of 2 speakers. Thank you.
Thank you very much. Okay, as far as I know, the next speaker is me. So I assume you know who is speaking, and I will speak about speech database and protocol validation. I don't see the mouse and how I get out. Okay, so we will use here a way to validate the database, and we will show that we can work in the waveform of the signals and calculate the entropies. This work was done with several friends from France, from ERICOM, and from ELIA, Avignon University. The motivation is that sometimes we have database and we need to train a system, and we want to know is the database we take for training the system represent well the data that we want to work with. So we have to evaluate if the train and the test data are from the same domain, if we want them to be from the same domain, or from different domains, if we want them to be from different domains. Basically, if there is a mismatch or not between the databases. So let's give first motivation of 2 small examples. Assume that the real data came from such GMM, one-dimensional 2 Gaussians GMM, and we want to make a PDF estimation. Of course, given the data, we can estimate the average log likelihood, which is very similar to the empirical entropy, and we can calculate it exactly. But now, if this is all the data and we want to take part for training and part for evaluation, if we mistakenly take this data for training and we train the parameters theta t from train, and we have some closed form of the average log likelihood, but then we take the data for testing, which will be like this, totally different. And they all were taken from the upper plot. So part of these points were taken for training and part of them for evaluation. And now we want to calculate the average log likelihood of the evaluation data given the parameters that were estimated on the trained data. And of course, the average log likelihood will be much lower because the train and the evaluation or the test are not matched. And we want to know in advance that we did something wrong and they do not match. Another example is for classification. We have two classes, and we have data from first class and second class, and we want to split them into two subsets. The training data was plotted down, and it's different from the eval data. Again, if we have a classifier, it will be a bad classifier because we train with one type of data and classify with, evaluate with another one. So in one-dimensional case, it's very easy because we can see, we can plot the data, but what happened when we in high dimension like speech? So we still want to have some feeling if we have a good data for training that fits the evaluation set. And when we are going to speech, we have different segment length and different environments and many other parameters, but the problem is what we want from this evaluation. Of course, this evaluation should be compared in some space, but do we want to compare it in the I vector space or MFCC space? The decision if we separate, whether we separate the data good or not, cannot rely on the features we choose, or we choose the subs that it's in a good way or in a bad way. So if we define the problem, we want to take the database and divide it into train, maybe development, and evaluation data sets such that they will be statistically balanced. We will speak about what it means statistically balanced. But the balance should be task independent. And it also doesn't mean that it should be similar statistics, because if you want to work in mismatched conditions, the databases should have different statistics, but we have to be able to see that they have different statistics. And if they are in matched conditions, we should see that the statistics are the same, approximately. So when we say that it's statistically balanced, we want it to be independent on the representation of the data. We don't care I vectors, MFCC, LPC, X vectors, R vectors. It should be data representation independent, and it should be independent of from our classifiers, PLDA, HMM, DNN, you name it. So the best way is to work on the data itself, because the waveform is independent from the future representation or features we use, and it's independent from the classifier. We work on the data itself. So if we look, for example, of one recording, we can see the amplitude. It was samples, this example in 16 beats with, so we have 2 in the power of 16 sampling levels, and we can plot the histogram or normalized histogram, which is PMF, probability mass function, and we can see that it's approximately a Laplace distribution as we know it. And we can, of course, calculate now on this distribution the entropy of this single recording. But now we can do it for each and every recording in the database. We can calculate the PMF and then calculate the entropy of each occurrence in our recordings. And then we can draw the PMF of these entropies and compare, let's say visually compare, because now it's one-dimensional. We can draw the PMF of entropies of the training set. We can draw the entropies of the evaluation set, and we can easily visualize whether the statistics is the same or not. We will show several examples of 4 databases: TIMIT, RSR 2015, anti-spoofing competition of ASV spoof 2015, which basically was on synthesis speech and speech conversion, and on anti-spoof competition 2017, which was basically on replay data. We can see on different databases how many males and females there were, and in the case of anti-spoofing, how many was bona fide and how many spoofed data recordings there were. So the representation, as I said, waveform is representation and classifier independent. However, different tasks can lead to different way of calculating the entropy. We know that when we use automatic speech or speaker recognition, we want to use VAD. So we calculate these entropies after using VAD. And for anti-spoofing, we know that the non-speech data is very important, so we usually do not use VAD. So we calculate the entropies, including the non-speech, without VAD. So TIMIT is a very clean database, small number of sentences in a very clean environment, and matched conditions. So we assume that the train and the dev conditions should be the same. And if we are looking at the histograms, the PMFs of the entropies of the train and the dev, and we see that they are matched very good. When we are going to RSR database, it's still a clean database, very clean, recording in good conditions, but they are not the same. For the dev set, for the evaluation set, several more equipments were used for recording. So there should be a small mismatch. And we see that there is a mismatch in data because not the same equipment was used for the dev set and eval set. This is an example that the condition should be a little bit mismatched, and we see it in the data. When we are going to anti-spoof 2015, we have to look separately for the bona fide speech and for spoofed speech. So we see that for the upper plot, train, dev, and eval are almost the same, which is bona fide. It's mean our natural speech, basically recorded in the same conditions. When we are talking about the spoofed speech, In the evaluation case, we wanted to see if the system can generalize to different synthesis and speech conversion methods. So in the evaluation database, there were several other techniques that were not seen during the training and the development. So there is a small mismatch between the eval and the other two subsets. And we can see that the train and dev are very similar, while the eval is a little bit more spreader, a little bit more heavy tails. So it's also a good example that we see that in the first case of natural speech, there should not be mismatch, while for the spoofed data, there should be mismatch. And now we are going to the evaluation of ASV spoof 2017. And I remind you, it should be on the replayed data. It means that there's no synthesis, no speech conversion. Someone record the speaker and then replay the data, and we can record it with different equipment and replay it with different equipment. And there were a lot of different conditions, a huge diversity. So there were very few examples for each condition. And let's look first at the lower plot of spoofed speech. We can see that PMFs are different one from each other, but they lay all in the same range. They span the same range of entropies. While we are looking at the upper plot of natural speech, we see something strange. The train and the dev span the same range, which are a little bit left to what happened in the spoofed speech. But when we are looking on the eval distribution, it's span the same range as the spoofed speech. We cannot explain why it happens, but we know that all the results in this evaluation were very bad. And now we can see why it happens, because the statistics of the eval bona fide speech was not the same as for train and dev, and the distribution of entropies was more similar to the spoofed data than to the real speech data. So it was unexpected. It wasn't done by purpose. It just when you shuffle the data, sometimes the coin flipped 100 times on the same side. And this what happens maybe here. We are not sure. But whatever the reason, it makes a lot of problem, and the partitioning was not well balanced. And now I want to show from a small database that we work on the coronavirus. We try to make a classification if people who are speaking are have coronavirus or not, positive or negative. The database was very small. 23 for train, there were 23 speakers that are healthy and 20 coronavirus, and test was even smaller. Each speaker record himself for several days in a row and for several tasks like saying ah or z or counting, reading. So we have quite a lot of recordings per speaker, and we see that at the bottom at the table that for the training data we have almost 600 recordings of healthy and 850 recordings for coronavirus, and for test we also have several hundreds of recordings, and we wanted to see whether the statistics is the same. On the upper plot, we see the entropy PMFs of the coronavirus train and test, and we see that they span the same range, but they're not see the same, looks the same. And the same for healthy on the bottom. We can see it even better if we plot the same histograms, but in a little bit different order. At the upper plot, we see the training data, health and coronavirus, and in the plot below, we see the test data. And what we can see that for trained, both the healthy and the people with coronavirus have unimodal distribution, while for the test, they have both bimodal distribution. So we see that the data is not distributed well between the train and the test. And we see the results of different groups that work, and the results were not good. We see a big difference between the results that were achieved by leave one out on the train and the results on the test. They were differ very much, and they shouldn't, because leave one out give us an example that was not in the train during the evaluation, and still the difference was very big. And we assume that one of the reasons is because the data wasn't separated in train and test in a good manner, and it's hard to do it when the database is so small. To conclude, we present a very simple and efficient way to see it, whether the database is divided in a good way. It's only a first solution, and there is a much work to do, but it's a protocol that can help to design the evaluations we want to do to train our systems. We saw that on TIMIT and ASV spoof 15 bona fide, the data should have be the same, because there are matched conditions, and we really saw it for RSR 2015 and ASV spoof 2015 spoof data. We saw the mismatch, and there should be a mismatch. While for ASV spoof 2017, we saw effects that we shouldn't see it, and it shows that there was a problem how we separate the data in our 3 subsets. And the same we saw for COVID-19 on a very small database. So, thank you. I see there is no questions. I see it's hard. It's our first trial with webinar, and yeah, it was a good trial, and maybe next time you will feel better to ask questions, and the flow will be better, but I think that still it was a very interesting one with very interesting talks by John, Deborah, and Elia, and we want to thank them all. And I hope to see you next time. Next year, I hope we will not do it in a webinar, but we can sit all together. And on Thursday, if you want to, there is an unsupervised machine learning seminar, and you are all invited to another webinar. Bye-bye.